We have the blue screen of death. Let me do this. And nobody will volunteer to be the. Okay, this will take a few minutes and I can get my slides up. The people online can see it for now. Let's go back. I'll go back and start to redraw that, what I had here. And then you guys can pick it up later. So where I was at was this was a voltage divider. I'm recording. Vn equals V sig. I'm rebooting my projector at the moment too. That's not my fault. Rn over Rn plus R sig. I've never seen it do that at the same time before. Okay, so looking at that equation, Vn equals V sig, Rn over Rn plus R sig. If we want to make Vn as big as we possibly can, what are we going to do? We have to make Rn big. If Rn's much bigger than R sig, if Rn's much bigger than R sig, then Vn equals V sig. And that's the best we can do, is get a voltage transfer efficiency of 1 right there. So I want to make Rn as big as I possibly can because of the laws of voltage divider rules. This is like a true DJ moment when the equipment's failing and you're still just holding it together. I've had to do this a few times. If we look at the output of that, and it's completely dead. Worst thing to have is dead air. On the other side of this, how much time do we have? What we have here is we have a dependent voltage source, AV times Vn, going into RO minus my times my load resistor. Okay. It is completely freaking dead. Instructor PC.
Wait, are they in series or are they in parallel? Or no?
They're in series. They share the same current. It's the same problem. It's out of this voltage source. But now we want RL is my V out. If I press buttons, eventually it will work. So in order to get this equation, this is amazing. Segue. In order to get what? I'm talking to two audiences at the same time. I'm sorry. In order to get the voltage across the output as big as I possibly can, now the equation looks like V out equals AV Vn times RL over RL plus RO. Right? AV, I'm going to stop writing in a minute. Vn RL over RL plus RO. So in order to get my V out as big as I possibly can, I want RO to be small. Because if RO is 0, this whole thing means V out equals AVBN. I don't have any losses. So this RO, I want to be small. The greatest thing you can know, what are the great, other than V equals IR, and as an analog engineer, is that for any circuit, I want a big input resistance and I want a small output resistance. And you see people like at Microchip trying to design ADCs that basically have analog interfaces to the real world, and they don't even specify what their RO is. And you just know it's bad because your circuit doesn't work. And if I put a larger load resistor across there, suddenly it magically works. Okay, real world stuff. They don't spec it. They're digital engineers, they don't know. What we've done so far is this, and you have no idea what I'm talking about. This is a piece of paper. If you call up the slide, you can't do that. If you call up the slides on VVLearn, you have a common source amplifier. It gives you a summary for all the different amplifiers, and we'll look at this one again. The input resistance of a common source is infinity. Its voltage gain, if I use that circuit, is minus GM big RO, and my big RO is RO in parallel with RD. And the rest of it is a summary of things we haven't done yet, so don't worry about it. We'll talk about this as we start filling this in. When this little slide right here can get you far, and I know on my exams, knowing that the gain, if you have to guess the gain, it's GM big RO, and maybe a minus sign will get you pretty far too. Oh, no, okay. We have pictures of circuits here. Oh my gosh. It's just, okay, what we're looking at here, okay, how much time do we have? We have 25 minutes. If you want to see the pictures, you're gonna have to call them up. I'm sorry. We're on slide 23. Okay, Amelia's got a laptop and you can like share. I'm giving everyone a minute to log in so that my lecture makes some sense to the 4 people in the room. I don't know what's going on. Okay. It's just not fun. Okay. Okay. We're on the slide that has a big 31 at the top. If you look at circuit A, you have an AC input on the gate. You have an AC, if you turn your sound off. Okay. You have an AC output on the source. The common, yeah, please don't interrupt me right now. The common terminal right now is the drain. So we call this a common drain amplifier, abbreviated CD. And someone's chatting at me and I just have to. Yes, thank you. That is exactly right, Chris Weber. Whoever's got the volume speakers on their computer. Okay, okay. You're not even on my Zoom. You're just looking at the slides. Okay. For B, basically my input's on the gate and my output is on the drain. So this is a common source with a pesky source resistor. If I put the input on the gate and the output on the drain, this becomes a common source. If I put the input on the source and the output on the drain, I've got a common gate. And we'll go through all 4 of those. We'll derive them, spend more time on the common source. I feel a little bit better now. People in the classroom can actually understand what I'm talking about. Right. I don't know what I'm going to say about that yet. Yeah, figure out what you know and what you don't. and how to perform to two audiences at once, and life will be good to you. If you can figure out those things that aren't really working so well for you, you can make it work. The big thing we want to know, given this amplifier, we want to know what is its input resistance, what is its output resistance, what is its gain. Really common exam question, ask you those three things, you can characterize the amplifier. The circuits may look a little bit different. There's more to life than just those 4 amplifiers I just showed you. There's things called cascodes and diff amps and things like this. The next slide is the one I was talking about in class where you couldn't see it. It's just a summary. I've never used this much because I found it's really easy to trick people on the exams by just getting rid of RD or renaming it RL. Or putting an RD and an RL in, and they don't know what to do because they think this chart is always right. It's right for specific circuits. So be careful with that. The more generalized way of doing this we'll get to. Oh, good. You guys will be able to see this. And we just did this. There is repetitive in there. I did this. Looking into the gate with the source and drain grounded, you see RN, this is for a common source, is infinity. No current can flow. If I switch that around and ground the gate and the source, then VGS is 0, which means this is 0, which means my output resistance looking into this node is little RO. If I put a drain or a load resistor in parallel with that, I'd have to take the parallel combination. Now there's this magic chart that I never knew about until I was teaching Dr. Brower's classes, and I came across this and I said, gee, that's amazing. That is like, would save me a whole bunch of time trying to figure this stuff out. This is the slide. There's more information on this slide than you can ever imagine. Remember, I told you you have to guess the gain. It's GMRO. This gives you RO. If I look into the drain of a transistor, the resistance I see is little RO. We just saw that on the last one. If I look into the gate, the resistance is infinity. And I'll convince you of this one later. What you see looking into the source of the transistor is it is 1 over GM in parallel with RO. Since 1 over GM is so much smaller than RO, it approximately equals 1 over GM. That's going to take some convincing. It's in here later when we get to one of the other amplifiers. Okay, so if I stick resistors in series with those contacts, and I actually look into the drain of the resistor, what I see is RO multiplied by this term, 1 plus GM times whatever resistance is hanging off the source. That could be a source resistor, it could be another transistor, it could be a lot of things. But looking into the drain of the transistor, that is pretty much the easiest way to figure out what resistance you see. Looking into the gate, you always see infinity. And looking into the source, you get this equation that I can never remember. It's 1 over GM times 1 plus RD over RO. And RD is the resistor that's up here. That is a mouthful for one day, but we will go through this in detail. If you can look into it, if you know looking into this transistor right here, if you know what resistance you can see, this is what's going to help you find your R's in, your big RN and your big RO. and we will go through a whole bunch of stuff using this. We'll review this. For right now, let me just, okay. So if we want to use this model to figure out what Rn and Ro are, instead of breaking it down and drawing the transistor model, if we apply this diagram here, the input resistance is looking into the gate. Looking into the gate, I see infinity. It's an amazing shortcut, if you believe it for now. Looking into the drain of the transistor right here, looking here, I see RD in parallel with the resistance looking into the drain. So my RO is RD in parallel with, I'll call it little RD, the AC resistance looking into the drain. The AC resistance looking into the drain is the RO of that transistor, RO times 1 plus GMRS. RS in this case is a 0 ohm resistor, so it is just little RO. So that becomes RD in parallel with little RO. And that's our big RO. It's a the diagram's a shortcut, and it can help you really get, when you have a whole bunch of these problems like you're doing homework, it can help you get there faster. And you can actually, one of the homework problems, no, I called up one of the homework problems in my head. One of the homework problems is you actually, for like a common gate amplifier, have to go through and draw the Thevenin equivalent circuits to figure this out. There are examples of this in the book, and that will help convince you too. Unfortunately, there's a lot in Cedra, and I don't have. I'm covering maybe, in this entire class, I cover maybe 3 chapters of Cedra. And if you think of the depth of it, it's a really deep, very thick book. A lot of stuff for you to learn. We did this. RO and RD are connected in parallel because this node is grounded, so these are connected together. They're in parallel. The current for GM VGS flows through the parallel combination. So my AVO, my V out over VGS, we've done this 100 times already, is I have a negative current. My VO, this is Ohm's law, negative current going in because my positive side's here, negative GM VGS RO in parallel with RD. And that's a D. And this is what we've been calling big RO. We almost done, yes we are. This happened to me yesterday too. You guys didn't walk out of the classroom. You're soft. So if I have a common source amplifier, my input resistance is infinity. My output resistance is RO in parallel with RD. My voltage gain is GM RO in parallel with RD. But now I look at this circuit, there is no RD and there is an RL. Let's only have a meeting in half an hour. So in this case, my RD is RL. Yeah. Putting these resistors into the circuit works really good for when I'm building something on a printed circuit board. I can't build resistors with any accuracy, and unless they're huge, inside an integrated circuit. So we've got to figure out a way to do this with transistors, and that will come later. Basically what I'm going to do is I'm going to take that resistor and I'm going to replace it with a transistor that is acting like a resistor. We'll get to that later. I should have just kept my mouth shut. Now, we're going to use the chart. I want everybody to figure this out on their own. Use the chart. Tell me what RN and R out is. I should almost send this video to Jack. He'd laugh at me. Okay, what are we doing here? What's the input resistance? It's infinity. The input resistance of every common source amplifier is infinity, and this is why I love MOSFETs. One of the reasons why I love MOSFETs. What's the output resistance? This is the harder one. I've got RD here, big RD. It's in parallel with the resistance looking into the drain of the transistor. If I use the chart, the resistance looking into the drain is RO times 1 plus GM of that transistor times whatever resistance I have on the source, and I've got an RS there, and this RS is big RS. Okay, what have I just done? My gain, I'm just going to declare this at this point. We'll do, I think we do some more on this later, is minus GM big RO. So what have we done here? Our old circuit without RS had RD in parallel with little RO. GM times R, let's get to some basics first. GM RS always turns out to be much greater than 1. It's a big number. It may be like 5. Okay, so what I'm doing here is I'm taking my RO and I'm multiplying it by a number that's bigger than 1. So by adding that source resistor, I've increased this part of little RO. I've increased little RO by a factor of 1 plus GMRS. I put a big resistor in parallel with a fixed resistor, and this number usually comes out to be bigger than RD. My RO is still about whatever RD is. I should not go into this. I'm going to go heavily analog on you. Some of you will understand this, probably not many. The purpose of that source resistor is it actually provides feedback in the circuit. Maybe hard to see, maybe kind of hard to see. It's going to decrease the gain and it increases the stability. And there's tricks to work around that. And I've just declared that and you guys don't know what I'm talking about. So my RO will go up as long as this number is bigger, as long as this number is bigger than a little RO. So I would need a big RD in order to make this work. This is what happens when I understand what's going on.
Julie,
yes, please ask me questions. Focus me.
Why is big RS equivalent to the little RO or the drain resistance on the example one, the example NMOS?
Oh, let's do that. That will be a wonderful way to spend the next 10 minutes.
Oh, okay, yeah, because I'm kind of confused because I don't get why you wouldn't just use RS.
Why you're okay? Well, let's not worry about that for a minute. Let's get to a big blank slide right here. Let's look at what happens when we put RS in the circuit. I want to convince you that that diagram's right, or at least on some level, and I'm going to hate myself for this. VGS, the gate, the source, GM, VGS, and little RO. Now, when we have the source resistor in there, I'm going to call this RS. This is the drain. We want to see what happens to the, oh God, I don't want to do this. Okay, sorry. I just realized how bad this is. What we're going to do is we're going to follow the rules of Thevenin. And I'll explain to you why you want to use the diagram. Following the rules of Thevenin, if we want to find the output resistance looking into there, what I would get to do is I would get to ground the gate. The source is already grounded through the source resistance, and deactivate any independent sources. Now I still have that dependent source in there. So the quickest way I know how to do this is I put a voltage here, and I'm going to call it V test. And I want to find that resistance. What I need to figure out is I need to figure out what I test is. And my Thevenin equivalent, V equals IR, R out is going to equal the ratio of V test over I test. Okay. So what I have to do is I have to do circuit analysis and figure out what that is. This looks like one of your homework problems. I'm sorry. VGS. Okay, so VGS here, if I do a Thevenin, if I do KVL around this loop right here, I get negative VGS equals, I don't know how to get there. I test. Let me look at this for a minute. I can do that loop. I can do this loop on the input. I think that will be more helpful. So V test, I'm just making this up. I have no idea. I'm doing this on the fly. V test, the current going through RO is I test. So V test minus I test RO plus minus the current going through this. Oh, no. I never mind. I don't want to do this.
Back to the feedback resistance, the reason,
Yeah.
the reason it acts as such is because the VG needs to stay constant and the source is just tied to ground.
Right.
So anytime it's changing current, the resistor has to kind of react.
The resistor, and it takes a little bit off the output to do that. And it stabilizes everything. It decreases the gain, but it increases the stability. Yeah. This is a circuit analysis. And you look, there's only 3 transistors in there. I could, what I would normally do in the real world is if I get a problem like this, I go into multi-sim or PSpice or something like that, and I convinced myself it works. I didn't like doing circuit analysis. I liked using simulators.
That's a lot better than like just trying to set the VGS constant outright because
Yeah.
then there's large variations.
Well, there is, oh, see, the thing you can't control in the real world is your VGS is coming from another circuit that has gain variations with temperature and has input instability. So if your VGS on the input increases by a large amount, your output could saturate and go into distortion. So they actually have this thing called automatic gain control where they go through, they sample the output, and if it gets above a certain level, you cut the gain by changing the bias point of the transistor. We look at those circuits. Oh, where do we do that? We do it in 490 in the fall a little bit, and I do it in my analog class. If you're really interested in analog, I've got a secret elective. But I think I am just completely garfing things up, and we need to reboot this and maybe get our projector back. I don't know what happened to it. It could have overheated. I'll call classroom support. Okay. That was enough to throw me off. And on top of that, I just, yeah, okay, never mind. It's time to call it a day. Let the 188 students have the lab, and so I can get to my silly meeting. Who's not? Zach Hoover, Danielle, and Gabriel Martin.
I'm here.
Hoover is here. I see you. Gabriel Martin, Danielle. Okay, you can complain or watch the video. Okay. Let's power this off. Yes. Is this thing going flashy when it's on? It's got that one red light.
Just turn off.
There is up on the top of the projector, like the ceiling side. There's a button. And sometimes I get 12 people to stand on tables and stuff. But I don't know. Maybe I'll just call classroom support at this point. And the next professor's a grad student. He doesn't deserve that. 928-523-8818. And he's a grad student I like. Okay, I'm going to stop recording.